Well, let's look at a very simple function that we want to find the inverse of if the inverse exists. Well, this function, we're going back to something really simple. Remember, a function is a set of ordered pairs where you can't have two ordered pairs with the same first component and having two different second components. So all of our first components are different here, 1, 2, 3, 4, so no problem. This is definitely a function. Well, the inverse would be this. Remember that step when you find an inverse, you replace x with y? Well, this is similar to that situation. All you need to do is reverse x and y. Reverse x and y. So 1, 2 became 2, 1. 2, 0 became 0, 2. 3, 3, this is interesting. That stays the same. And then 4, 6 becomes 6, 4. Well, could this be the inverse function of f? F inverse equal question mark? No. The only reason it's not is because this is not even a function. 1, 2, oops. 1, 2, 2, 0, 3. Yes, it is a function. What am I talking about? My mistake. I was thinking this was not a function. I misread one of the numbers. Let's see. I want to make sure. I've got a 2, 1, and nowhere. Yes, all of my beginning numbers are distinct. All of my x values. 2, 0, 3, 6. So this indeed is a function. Therefore, it is an inverse, the inverse of the function f. If we had a situation where we had something like g being the ordered pair 1, or having two ordered pairs, say 1, 2, and negative 1, 2, this is certainly a function, maps 1 to 2, and it maps negative 1 to 2 as well. But if this were invertible, if it had an inverse function, it would be 2, 1, comma, 2, negative 1. This is not a function. So we could say in this case, g has no inverse function. This is a function, but it does not have an inverse function. Okay, so now let's look at something called the horizontal line test. I think we already know about the vertical line test that helps you determine if a graph is a function. The horizontal line test tells you whether a function has an inverse function. A function f has an inverse function if there's no horizontal line that intersects f more than once. Or at more than one point. Okay, so let's just look at graphs for a second. Is this first one, it looks a little bit like f of x equals x squared. And we did that in the previous video. Remember, it did not have an inverse. You can draw a horizontal line that crosses it twice. Therefore, no inverse, because it crosses it more than twice. Can you find any line, horizontal line, that will cross this function more than once? Of course not. This is a straight line. So yes, this function has an inverse. I'll say has inverse. This one, no. You can find a horizontal line that actually crosses it 3 times. 1, 2, 3. So no inverse. This one kind of hard to tell, but it kind of looks like this is going uphill for the rest of its life as it goes to the left, and this one going downhill to the right, uphill to the left, downhill to the right. So it looks like there's no horizontal line that would cross it more than once, so has an inverse. It is invertible. And notice, let's go back to this little example I made up here. If you were to graph this function g of 2 points, hope you can see this, it would be 1, 2, and negative 1, 2. Just 2 points. Do those 2 points pass the horizontal line test? No. You could draw a horizontal line right through them. It crosses it twice. So that function does not have an inverse. All right, well, a function passes the horizontal line test. I think we've already discussed this. If no two-ordered pairs have the same second component, and when you have that situation, the function is called a one-to-one function. So let's one more time. Let's go back up here. A function passes the horizontal line test if no two-ordered pairs have the same second component. Do any two-ordered pairs here have the same second component? No, not at all. Oops, up here, I should have looked up here. 2, 0, 3, 6. No. So therefore, this has an inverse. And if you look at the inverse function, well, of course, if this one is the inverse of this, then f is the inverse of f inverse, which is interesting. I guess I could have noted this before, that f inverse of f, oops, let me write it again. F inverse is equal to f. Because f inverse is, after all, this guy right here. If you take the inverse of him, you're going to go right back here. So let's get back to horizontal line test. Another simple function. Here's a function with 3 ordered pairs, 0, 1, 2, 3, 4, 1. Is it a function? Indeed it is. You don't have any ordered pairs that have the same first component. So therefore it is a function, because it would not be a function if you found something like a 0, 1 and a 0, 2, where you have the first component the same, and in the ordered pairs the second components are different. So this is indeed a function. But is it one-to-one? In other words, would it pass the horizontal line test? Well, it's not one-to-one. You can see that 0 gets mapped to 1 and 4 gets mapped to 1. So that's not a one-to-one. If it had an inverse, it would be 1, 0, 3, 2, 1, 4. But this is not a function because it has 2 ordered pairs, both starting with 1, x values of 1, getting mapped to 2 distinct numbers. So I'm going to say this is not a function. So would it pass the horizontal line test? No. Is it one-to-one? That's asking the same question. No. Because remember, when you plot this point, 0, 1, the height of the function is 1 at 0. Over here, 4, 1, at x equals 4, the height of the function is 1. You could pass a horizontal line through both of these 2 points. So it is not one-to-one. It would not pass the horizontal line test.